each component piece by piece and explain it. Talk about functions, why one design is advantageous in a given application, and so on. We are also going from end to beginning because it will help a lot in finding purpose in every piece of information. For example, why should I care about the quality of the air? One can argue I just need the pressure to move my piston inside the cylinder. Do the work and that's all. We will see there are requirements for components, and if we talk about specifications first and purpose second, then even if you give all your best, information won't stick very easy. So we will start talking about actuators. They are of two main types, the linear actuator or the pneumatic cylinder and the rotary actuator. The pneumatic cylinder is also divided into two main types, single acting and double acting. Let's start with the symbol. Imagine it as an oversimplified cross-section of the cylinder. We take a rectangle, that is the cylinder. We put ports on either side. That's the in and out pathway for the air. Next, we symbolize the piston inside and finally the rod. A double-acting cylinder is a cylinder on which we can actuate both the advance and the return strokes. This can be seen on the symbol as both advance and return chambers have their orifice drawn. This is then divided into a few more types. So, in terms of construction, we have the standard double-acting cylinder, double rod double-acting cylinder, and the rodless double-acting cylinder. We can see how each one is different from each other just by looking at the symbols. A single-acting cylinder is a linear cylinder in which only one stroke is considered functional, and the other is a passive return stroke under the action of the compression spring. We can see the difference in the symbol given there is a spring and there is only one input hole. It is also divided into two types, single-acting spring-extended cylinder and single-acting spring-return cylinder. As we can see from the symbols, the difference is in the function of the spring. The rotary actuators are used to obtain a rotational movement. They are also divided into two main types, continuous rotation and semi-rotation. The continuous rotation actuator gives, as its name says, a continuous rotation for which we can measure an RPM and a torque. It is encountered less in industrial applications. They can serve as a pneumatic screwdriver, drill, and so on. Here it rivals the electric motor, and even if it has its benefits, unless there is an explosion hazard in the work environment, the electric motor is preferred for added precision and control. On the other hand, the semi-rotary actuator is a lot more popular. It is an actuator which has a limited rotational stroke, usually between 0 and 270 degrees. Actuators are the workhorses of the pneumatic systems. They convert elastic potential energy stored as compressed air into mechanical work. Like in any other type of movement in the universe, every system tends to stay at an equilibrium. If an imbalance appears naturally, it will want to balance itself out. In pneumatic actuations, there is the need to balance the higher pressure compressed air with the lower atmospheric pressure. In electric actuation, there has to be a difference of potential for it to work, A plus and A minus. Think of it as you taking on an arm wrestling. The necessary force is the force with which you overcome your opponent. If you have the same force, the hands are not going to move. But if there is an imbalance, the stronger one, you or your opponent, will push the weaker one until equilibrium is obtained and you hit the table or touch the table. In this animation, We can see there is an imbalance between the pressurized advance chamber and the atmospheric pressure in the return chamber. This is how pneumatic cylinders work. They convert pressure into movement. This is a less of a theoretical course, but in any case we still have to graze a little the surface of theoretical pneumatics. The base formula for calculating the force of a pneumatic cylinder is force equals pressure times area. Now, if we take that and break it down for a circular area, the formula is force equals pressure times pi times the radius of the piston squared. This formula is valid only for calculating the force on the chamber without the rod, or both chambers in case of cylinders without rods. If the side of the piston for which we are calculating has a rod, the area will decrease. So the formula is force equals pressure times pi times the subtraction of the squared radius of the rod from the squared radius of the piston. Now let's calculate a simple example. I encourage you to try it on a piece of paper. A pneumatic cylinder has a bore diameter of 15 millimeters, a rod diameter of 20 millimeters, and the pneumatic system provides us with 0.5 megapascals of pressure. Calculate the advance and return forces. First, we take the advance force. Force advance is 0.5 megapascals times 3.14 times 25 millimeters squared. That equals 0.5 megapascals times 1926.5 millimeters squared, and it equals 981.25 newtons. Secondly, the return stroke. Force return equals 0.5 megapascals times 3.14 times 25 millimeters squared minus 10 millimeters squared. It equals 0.5 megapascals times 3.14 times 525 millimeters squared, which equals 824 newtons. I encourage you to calculate a few more just to get yourself used to the procedure. A pneumatic cylinder has a bore diameter of x millimeters, a rod diameter of y millimeters, and the pneumatic system provides us with z megapascals of pressure. Calculate the advance and return forces. I want to ask you a question. Which one do you think is better? The single acting or the double acting? With either one of the answers, you are both right and wrong. Every type of equipment has its upsides and downsides. For us, to judge which is better, we need an application to give us some context. For example, it's not recommended to use a double-acting cylinder for a machine which has power-saving requirements. We need to pressurize both the advance and the return stroke, and a single-acting cylinder, we cut the air consumption in half. On the other hand, if we have a robotic arm, it is better to use a less heavy double-acting cylinder. For this construction, you can observe the differences between the two types of cylinders. The single-acting cylinder is usually constructed from the same components as the double-acting cylinder, but adding a compression spring, a stroke limiter to limit the compression of the spring, and a simple air filter on the passive orifice, which would pressurize the spring chamber. Single-acting. Advantages: less air consumption, one less stroke to pressurize. In the absence of air, the cylinder has a well-known defined position. If there is a problem with the pneumatic system and there isn't a supply, we might have to design the machine to have a preferred position in case of emergencies. Another advantage is the simpler directional control valve needed for actuations, which is a 3-2 instead of a 5-2. The disadvantages of the single-acting cylinder that it has short strokes and diameters. Because of added complexity, They are usually manufactured to a limited dimension. Another disadvantage is that the spring gives a counterforce, lowering the efficiency. Also, speed controlling is harder to achieve. It has a higher purchase price given its higher complexity, and it has higher mass given it is more complicated and has more components. Now, the double-acting cylinder. Advantages: larger diameters, longer strokes, lower purchase price, less mass. Disadvantages: actuation force differs between the strokes, more complex directional control valves needed, and in long strokes the rod may buckle. Now, let's see a few applications and how to weigh them in. In the first example, we are talking about a clamp with which to hold a piece for drilling. In this example, it is recommended to design the machine with a double-acting cylinder for both the actuation of the clamp and the lowering of the drill. In the case of the clamp, to output the same force, a single-acting cylinder would have to be larger to compensate for the spring counterforce. For the drill, it is also better to use a double-acting cylinder to develop the same force for the drilling bit for the entire stroke or the entire hole. Otherwise, the compression spring would modify the pressing force and the machine might have to suffer from uneven surfaces, longer machining times, or you would have to factor in the spring and choose a much bigger cylinder. In the second example, we are talking about a machine which feeds parts for stamping. This time around, the movement is less sensitive to speed and force variation, given you need just to move a piece from a feeder to a fixed, well-constrained position. Also, the stamping only needs to press a rubber end on the part to leave an ink mark. We can see in this example that a simple acting cylinder is more advantageous because the action of the spring doesn't influence our movements, at least not in a way we have to overcompensate for it. This way, we also benefit from energy saving, since we only need to pressurize one chamber. The final example is referring to a gripping hand on the end of a robotic arm. Should we use a single-acting cylinder, we would add more mass to the arm compared to a double-acting cylinder. One very important aspect of robotic arms is mass reduction. The more you get away from the base of the arm, mass has a bigger influence on accelerations, decelerations, also max load, max speed, and precision. If there is more mass at the end of the arm, this propagates through the entire arm, asking for more powerful motors, higher rigidity, stronger connecting elements, and so on. You can see how shedding every bit of mass possible at the gripping end gives you a better robotic arm. Because of that, not only is the double-acting cylinder a better choice than the single-acting, but also, being the easiest and cheapest type of conventional actuation, it is the best option in 90% of the cases. Side info: the remaining 10% is electric hydraulic actuation because sometimes higher precision is needed. Again, I encourage you to take a walk in your factory and keep an eye out on how single and double acting cylinders are used. Look for use case scenarios. Figure out why and how each one is a better choice than the other in a particular application. If you don't work in an industrial setting, I encourage you to get on some tours if available, or you can have a peek around the internet looking for industrial pneumatic actuations. There are times when using one type of cylinder is not practical or not even possible. When using a rod cylinder to move a part, we expect it to almost double in length while extended. What if there isn't enough space to make it possible? Or what if the cylinder for a given task needs to have a larger diameter than we can accommodate for? Let's take a look on other types of linear cylinders that we can find on the manufacturing plant. We will also have a look on how they work and the advantages they bring to the table. 1. The double rod cylinder is a cylinder which has the advantage of being able to take higher radial loads than single rod cylinders. Also, it can work both as a fixed body or a fixed rod. 2. Compact cylinders, as their name suggests, are more compact lengthwise, being designed with less bulky caps. But because of that, they are very sensitive to radial loads and they are limited in speed. 3. Rodless cylinders. These are cylinders which work without a rod. On the outside of the cylinder, there is a sleeve which follows the movement of the piston in one of two ways: mechanical coupled or magnetically coupled. The mechanical coupling needs to open and close a pneumatic seal which works similarly with a zip from a zig bag. This construction is prone to defects and pressure loss. If you need a rodless cylinder, it is advised to use a magnetically coupled one, as they are more robust. Other designs seen in manufacturing plants are of special cylinders. Here we can talk about axial tandem cylinders, which double the output force, keeping the same diameter. The one thing you should be careful about with these is that even they have the same diameter, they double in length, as you can see from the image. So, if you have an application where radial space is limited, but length is not a problem, this might be a solution for you. Another one is parallel tandem cylinders, which double the output force, keeping the same length. Maybe you are limited in length and height, but have enough space for a wider cylinder. This solution offers you double the force, but it is double in wideness. And another special type of design is anti-rotational cylinders, which are constructed with profiled rods or have an oval-shaped piston. There are operations like pick-and-place machines where it is very important for the rod not to rotate. In that case, an anti-rotational cylinder is the best solution for you. These special designs we are not going to cover in this basics course. They will be covered in a more advanced course with animations and calculations and everything there is need to know about them. But for now, it's good to mention them and for you to know about them. In case you need them, you know what to look for. I again encourage you to go through your manufacturing plant and look for cylinders, observe their purpose and think about the reasons they are used. If they are not the conventional type instead of the standard pneumatic cylinder. When a piston rod assembly accelerates its load to a certain speed, it builds up kinetic energy. For it to stop at the other end, it needs to dissipate the build-up kinetic energy. If it stops suddenly, then we cause stress on the parts that lower the lifespan of the entire cylinder. In extreme cases, it can even break violently. For example, if you are going in a car at 100 kilometers per hour, 60 miles per hour, and you stop suddenly in a wall, the car will crumble, the wheel will suffer, and most importantly, you will be very hurt, to say the least. On the other hand, if you use the brakes to stop in a longer distance, there is barely anything wearing out. The brake pads and the tires will do so a little bit. Taking the before mentioned example, we can extract that we need to be able to stop the piston rod assembly decelerating before it meets the end cap. There are a few ways available on the market to do so. First, easiest and cheapest solution comes in the form of a simple rubber bumper on each cap to take the impact away from the metal components. It's mostly present in lower diameter cylinders, as it improves over having nothing, but isn't enough to take on higher amounts of energy. Second, and the most used solution, is the pneumatic cushioning. When the stroke approaches either end, there will be an air cushion which will slow down the piston dramatically. First, when we supply air to the advanced stroke, the chamber will be pressurized directly through one-way seals. When the piston reaches the end of the stroke and the bushing meets the one-way seal, a counter pressure will be built up between the piston and the cap. This excess pressure will momentarily be higher than the supply, and this effect will give a backward force which will slow down the piston. The counter pressure will be released to the exhaust port, passing an adjustment needle. The adjustment needle, of course, gives us the flexibility to get a lower or higher cushioning effect. It can even stop the air from getting out and stop the piston short of the end. Third, there are hydraulic dampeners available on the market. This solution is also widespread and used more with rudderless cylinders, but it can also aid the pneumatic cushioning in usual cylinders. They work by squeezing the hydraulic oil through some very small holes, called capillary holes. As the stroke of the dampener progresses, one by one, the holes are covered. This gives us a characteristic of progressively higher dampening. After the force is removed, when the piston goes the other way, the hydraulic dampener returns the start position, aided by a small spring inside. When pressing a hydraulic dampener with your finger, it will not oppose your force very noticeable. It does not react to force, it reacts to impact. So, it will absorb kinetic energy of higher speed, but will mostly be ineffective against slow-moving mass. As usual, it is best, if you have the opportunity, to go through your factory, look around, and identify each type of cushioning there is. If you are a student, ask one of your professors to show you every type of component talked about. This way, you will grasp the information even better. Analyze why it is used in a given process, take a look on a data sheet, and see how the amount of energy is positioned in the manufacturer allowable kinetic energy table. There are manufacturing processes in which we need to flip a part 180 degrees, or turn it just 90 degrees, bend a piece of material to a certain angle, and so on. For example, a high to low diameter adapter needs to have its holes tapped. Given the holes are of different diameters, it will be done at distinct points with distinct tools. First, the bigger one is tapped. Afterwards, down the line, when the time comes for the smaller hole, it needs to be turned 180 degrees to position it correctly. The fast, cheap, and easy way to get it done is using a rotary pneumatic actuator. To be able to do an angular motion, the pneumatic components manufacturers have developed two main designs of rotary actuators: rack and pinion construction and the vane construction. A rack and pinion construction is based on a regular cylinder, the difference being that there are two pistons inside, joined by a rack, which turn a pinion positioned in the center, which is joined by a shaft perpendicular to the cylinder body. The advantage is that it can develop higher torque, greater stroke angles, and better cushioning ability. The disadvantages are that it takes more space and the rack and pinion mechanism suffers from backlash. If you watch closely when the direction changes, there is a very small distance which the rack has to travel before hitting the teeth of the pinion. This gives a small play. Nothing to worry about unless your manufacturing process requires very tight tolerances. The vane type is working by pressurizing a chamber which pushes a paddle in a circular motion. You can see from the top-down view how it happens. With the paddle, a shaft is receiving torque to rotate in a given angle. The maximum angle this type of construction can achieve is 270 degrees. In the real world, this stroke can be adjusted from 270 degrees downwards. If you require an angle of 90 degrees or less, you can double the torque output in the given size component by using a double vane design. The vane type is, of course, less powerful and the angular movement is limited to a maximum of 270 degrees. But on the other hand, is smaller in size, has less mass, and it doesn't suffer from backlash effect. Let's see how to choose between the two types when confronting with the dilemma. Even if, for the most part, either one will do the job, there are fine details, given their advantages and disadvantages, with which we are able to make a better design. So, if we have a stacking table with multiple positions and we have to rotate it 90 degrees, it is important that we choose the more precise option, looking at the problem of picking the parts at the next process from the rotated table. Therefore, we would be better off in going with the vane type, as it doesn't suffer from backlash effect. And very rarely you will see the need for a rotation higher than 270 degrees on a table. Also, if you are planning to add a rotation movement to a robotic arm, we should always be looking for the less mass option. In this case, the vane type is still providing us the best solution, as long as the rotation doesn't need to be more than 270 degrees. An example in which rack and pinion is superior is when we have to rotate a more massive part. If we want to rotate a metal bar, it will give a very high torque resistance, as the further away the mass is from the center of rotation, the more torque is needed to rotate it. Therefore, in this example, a rack and pinion style actuator will give us a better result. Of course, as always, I encourage you to take a walk through your factory, keep an eye out on how and where rotary pneumatic actuators are used. Look for use case scenarios, figure out why and how is every one a better choice than the other. Even if the pneumatic actuations are the simplest, they still have requirements you should watch out for. 1. As in any mechanical system which has moving parts, you should take care of friction. In time, the seals wear out, regardless of the material, rubber or metal. To ensure the seals hold the test of time, we have to talk about lubrication and reducing the friction force. Now, think on how would a piece of rubber slide on a metal surface when dry versus wet. Second, air quality. Poor filtered or non-filtered air will clog thin air passages, sound dampeners, or, in combination with lubrication, small particles will form gunk inside the cylinder and will lower the performance. Another contaminant is burnt oil from the air compressors. You might say it is very good. More oil, better lubrication, right? The reality is that burnt oil doesn't have lubrication properties anymore. It even causes damage to the rubber. And lastly, water contaminant. This one washes the lubrication. If metal has iron in its composition, it will develop rust, and if the work environment is below freezing, even ice will appear. 3. Counter pressure release. Most overseen problem by beginners is not thinking to release the counter pressure. To get movement in pneumatics, electric, or hydraulic actuations, one needs to make sure there is a difference of potential. Lower and higher pressure, or high voltage and ground. To understand the need better, think that you are arm wrestling again. To win, you will have to output a force bigger than the one your opponent is outputting. Now compare that with an arm wrestling, exactly the same, but you have a third guy pulling your arm in the other direction. You can call the third guy a counter force on your output. 1. To provide lubrication, we, of course, use a lubricator. In short, It is a component that holds oil in a bowl from where air receives drips very slowly at set intervals of time. Now that the industry has reached its maturity, there are readily available pneumatic cylinders which do not need it anymore. These cylinders are coming from the factory pre-lubricated for life. This is the life of the component, not the life of the user, of course. This is done by using a high-performance lubrication borrowed from the aviation sector. If you buy cylinders pre-lubricated for life, it is very important not to lubricate them further. The oil will wash away the high-performance lubrication, and you will need to provide lubrication from there on. All in all, air quality is the most common reason why pneumatic components break down. If we do not respect the manufacturer's air quality requirements, the cylinder and other components will fail. Even worse, at this point the warranty is voided. When specifying the purity of air required, the standard must always be referenced, followed by the purity class selected for each contaminant. An example on how to write an air quality specification is ISO 8573-1 on 2010. Let's say class 121. ISO 85731-2010 refers to the standard document and its revision. The 3 digits refer to the purity classification selected for solid particles, water, and total oil. Selecting an air purity class of 1 to 1 would specify the following air quality. Class 1 particulate. In each cubic meter of compressed air, the particulate count should not exceed 20,000 particles in the 0.1 to 0.5 micron size range, 400 particles in the 0.51 micron size range, and 10 particles in the 1 to 5 micron size range. Class 2, water. A pressure dew point, PDP, of minus 40 degrees Celsius or better is required, and no liquid water is allowed. Class 1, oil. In each cubic meter of compressed air, not more than 0.01 milligrams of oil is allowed. This is a total level of liquid oil, oil aerosol, and oil vapor. At this point, it had to be mentioned, but we will explore the air quality system further when talking about air preparation units. 3. When pressurizing a pneumatic actuator, linear or rotary, and it looks like it doesn't work or works only one way and not the other, it might be that the inactive chamber is still pressurized and holds the piston balanced. A very common mistake made by beginners is not accounting for the need. To drive the cylinders, we use the directional control valve. It distributes the pressure where we need it, advance or return chamber. Afterwards, it evacuates the compressed air from the other chamber to the environment. As long as we do the correct connections of tubing, this problem should not exist. But if something doesn't seem to be working, then take another look on how everything is pressurized.